I want to take a look at the two-way layout without interaction. Specifically, the question of what's the expected mean square of an effect. Now, the two-way layout without an interaction is a model where you describe the y's as a function of an overall mean plus the effects of each of the two factors plus a random effect, or a measurement error or a random deviation, if you like. We're going to assume, as usual, that our random component is just like a measurement error. They're independent, they're identically distributed, they have a fixed variance, and I've written normally distributed, although that's not necessary in what we're using here. The case we're taking is an equal replicate two-way layout. So in other words, the number of measurements in each ij cell is a fixed number equal to capital K. Some people denote this by a lowercase n. I like to use n as the total number of measurements. So n in this example is ijk. And we're using n for only that in this course. So the analysis of variance table basically has a column for each of the effects, how much is explained by the first factor, the second factor, how much is the residual error, and this adds up to a total. And if you go through the usual projections and stuff, or otherwise derive the sums of squares, then the sum of squares explained by factor A is this quantity here. The mean within each level of the factor minus the overall mean squared summed over ijk. Now, this is fixed in j and k, so it's just a multiplier. J and k come out as multipliers. Same thing happens with b, and then the total sum of squares without any correction, in other words, assuming no model except an overall mean, is this quantity down here. So the sum of squared errors, the unexplained sum of squares, is the difference between the two that are explained and the total. So our task today is to try to figure out what the expected value is of the mean squared error, the mean square explained by factor A, expected value of MSA. And we know that if the null hypothesis of no effect is correct, in other words, if all of these alphas here are 0, then the expected value of MSA is sigma squared. We're interested in the general case, what happens if there is an effect, what's the expected value of MSA then? And so we're going to look at these terms. The MSA is the SSA divided by I minus 1. SSA is this quantity here. So just start with what's inside the sum. So we start with y bar I dot dot minus y bar dot dot dot. So take the mean for main effect A in group number I and subtract the overall mean. Expand the squares as usual and then look at each term separately. So let's start by y bar I dot dot. Then we take y bar dot dot dot, and then we take the product of the two later on up here. Take the expected value of each one separately. Now when we look at y bar I dot dot, I mean this is in the context of a specific model. It's in the context of this model up here. So when you take an average across k and j, these don't change, but you get an average of the betas and an average of epsilon within these two categories. So that's in the usual notation, just beta bar and then epsilon bar averaged across the two categories. Now we're going to assume that the sum of the alphas over all i's and the sum of the betas over all j's are equal to 0. If they weren't, we could incorporate the average into mu. So we can safely assume that this is 0. So the average, the expected value of y bar I dot dot is just mu plus alpha I. Similarly for the variance, now this is the only variance coming into this formula here is the variance of epsilon bar I dot dot. Now this is an average over j times k IID random variable. So the variance is the original sigma squared divided by j times k. So we have these two. Now then we also know that the expected value of a quantity squared is just the variance of that quantity plus the expected value squared. And using the above two lines, this one and this one, we then come down to this result. It's sigma squared over jk plus mu plus alpha I squared. And we'll leave this the way they are for now. Next, take a look at the other part of the deviation here, y bar dot dot dot. So that's the mean of the y's across all of the factors, all of the levels. And this then is just the overall mean plus the average of the alphas plus the average of the betas. We're happy to assume that the average of the alphas is 0 and so is the average of the betas. Now remember that the epsilons are normal 0 sigma squares, independent. So the average, the expected value of those is 0. So the overall expected value is just the mean mu. And the variance, of course, is the sigma squared divided by total number of observations, which we can write either as n or ijk. And then again, the expected value of a quantity squared is the variance of that quantity plus the expected value of the quantity squared. And we've now just shown that this is equal to this number here. So what we're left with is the devious product, which is nothing fancy. You don't need the Nobel Prize to derive this. You just need a lot of patience. So the expected value of this quantity then isn't just the product of the two expected values, because y bar dot 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 includes the ith observations. So we need to be careful here. So let's write this out step by step, the product of these two terms. One of them is the average across j and k within the ith group. The other one is the average of all the observations. Now we cannot use the same I here as here because this I is fixed. This is in a sum across all I. So we use I prime to denote the second one. And now we need to be careful because of these I primes, some of them are equal to the I over here. So split this sum into two parts, depending on whether I is equal to, whether I prime is equal to I or not equal to I. So here we split it up into two parts, and now we can multiply this overall sum that we see in the second parenthesis from here to here, multiply it by this sum. The first part is the same, so we get this quantity squared over here. And then we get the sum of the two parentheses. Now, in the first part, we've got a quantity squared, and we know how to deal with this. This is going to be a variance plus a mean squared. The second part, these two terms are now independent because there are no common terms in them. And we know that the expected value of the product of independent random variables is just the product of the expected values. So we can take the expected value of each term separately. For the first part, well, to make life simple, let's go back to the y bars. This is the sum of I times j terms. And here we have a jk squared. So if we take the jk squared into this parenthesis, we get a division by jk. So that's back to our y sub I dot dot squared. And we do the same thing in the other part. We take the jk and divide it into this term to get y bar I dot dot. And then we can take ijk into the second part. Sorry, we take jk all the way into here. And we get I prime dot dot. So these are our two terms now. To take the expected value of the whole thing, we get on the one hand, we get the expected value of this part, which is here. And in the other one, we get the expected value of this y times these guys, which is the expected value of or the product of the expected values. And now to bring these things together, we know the expected value for square is the variance plus the square of the mean, and that's these two terms. And here we just have the two expected values, y plus mu plus alpha I and mu plus alpha I prime. And now look at these, what we have here. On the left, we have mu plus alpha I squared. Here we have mu plus alpha I also. We take this outside. And then we left with the sum without the ith term and the ith term itself. So in total, we get the sum over I prime, for I prime over all the values from 1 to capital I. And what this means then is that when we sum this up, we can add up the mu's, we just get I times mu, we add up the alpha I primes, we get a 0, and we're left with sigma squared over ijk from this term over here, and then we have mu plus alpha I times I mu divided by I, which is a mu squared plus mu times alpha I. And now we're ready to bring all these three terms together. So we have the expected value first here of y bar I dot squared. Then we have the expected value of y bar dot squared. And then we have negative 2 times the expected value of y bar I dot, y bar dot, right? So, so this is our sum, our expected value. Now we take the terms together. We have a sigma squared here. We have a sigma squared here, we have a sigma squared here. Bring all of these together into this term. Then we have a mu squared in here, a mu squared in here, minus 2 mu squared in here. So then all in all, that gives us a big 0. Then we have a mu times 2 mu times alpha I here, which is this term. And in the end, we had a negative 2 mu alpha I, so these go away. And then we left with only an alpha I squared over here. So what this ends up being is sigma squared times I minus 1 over ijk plus alpha I. So let's add all of this stuff together then. And the SSA, the MSA is SSA divided by I minus 1. So the expected value of MSA is the expected value of SSA, which is this stuff. Remember, we had a sum. We have a j times k in front of it from way up here, jk times the sum. So, and then we have the individual terms which we've just been dealing with. So these squares are what we just derived, these things, and we get rid of the 2 mu alpha i's, of course. And then we have the sum of the alpha I squared coming in here, and this is constant in I, so we just get a capital I times this term here. And the two i's, capital I's, cancel. The I minus 1 cancels in this term, and the jk's cancel in this term. So here, the expected value of this guy is, we're not supposed to have an expected value here anymore. We did that. So get rid of this stuff. So we just get a sigma squared for the first part, and that's nice. And then we have a jk over I minus 1 times this term. So the expected value of MSA overall is this quantity. And let's look at this for a minute or two. If the null hypothesis is true, then all the alphas are 0. That's the null hypothesis of no effect for factor A. And in that case, this is an unbiased estimate of sigma squared. And this is what we use when we derive the properties of the F statistic. The F statistic for the null hypothesis of no effect of factor A is exactly MSA divided by MSE. And of course, these both need to have an expected value of sigma squared for that to be an F statistic. It's not enough, but it's certainly a requirement. Secondly, you'll note that if the null hypothesis is false, then these alphas are non-zero, and the squares will be positive. So the expected value of MSA is larger than sigma squared. So this is equal to sigma squared if and only if all the alpha i's are equal to 0. It's greater than sigma squared if any alpha I is non-zero. Okay, so in other words, we want to reject when the MSA is too large, and that's exactly what we do with the F-test. We reject if the F statistic is too large, and that corresponds to an indication that one or more of these alpha i's is non-zero. So that concludes this discussion of the mean square for factor A in the two-way layout. Pretty much the same approach applies to the one-way layout, and of course the exact same by symmetry applies to the effect of factor B in the two-way layout. This is without interaction. With interaction, you would go through the same sort of algebra. It just becomes a little bit messier than it is here.